Hello and welcome to another video. We're discussing topic 7, where we are continuing our discussion on the t-test. This time we are looking at the t-test for dependent means. We have had our discussion and introduction to this already. In this video, we're going to call it part B, where we are just going to work through an example by hand and see that it is really very similar to the single sample t-test. Very, very similar. So this should go fairly smoothly. We are looking at the same textbook as always. Love this book, Statistics for Psychology. We're going to be on page 268, and I think we are looking for, 267, sorry, number 16 here. As a first example, they don't tell the whole story. They just summarize all the information for me, just for convenience to get me going. And we can perhaps look at a more story one, so to speak, in the future. For each of the following studies, using difference scores, test the significance using a t-test for dependent means. So the only issue here, I'll give you a little example. In number 19, for example, they give you more of a story where we are measuring the participant before and after treatment of some kind. It doesn't really matter. Let's look at this. Let's look at this one. We have a before and after situation. So the scores are dependent on each other. They're not independent. They're not completely separated from each other. Person A score is 20, and the after score is related and connected to that before score. I don't know exactly how, but I cannot assume an independence here. So we're in the situation of a dependent means comparison before and after. I want to see, is the average score before different from the average score after? Has there been a change of some kind? When the scores depend on each other, what we're going to do then in the dependent means case, which is where we are, we're going to calculate the differences, the difference scores, after minus before, after minus before, after minus before, and look at the distribution of those in the same way as a single sample. So in a way, I'm merging these by way of differences, and then I'm back in the single sample t-test. So they've summarized 17 over 16. They've summarized the information for me. We'll just do part A, where I don't need to know the story. The difference scores have been calculated. The mean has been calculated here as a 3.8. The variance has been calculated for that sample of difference scores. I'm interested in a high-tail test on the right, one-tailed test at an alpha of 5%. So let's just set this up with our familiar hypothesis testing steps. We have our null hypothesis, we have our research hypothesis, and in this case we're testing if the mean difference is more than if there is a mean difference between before and after. Now remember, this is after minus before. So one of the first things here is that we're always going to test this against 0. If there is no before versus after change, then the mean is going to be, the mean of the difference scores will be 0. That's our null hypothesis, no change. no change. But if there is a change, and in this case I'm looking for a positive change, that after there has been an improvement higher in the scores, then we're going to look at the mean differences, the mean of the differences. I'm going to get the right words here to be positive, meaning after minus before is positive, after greater than before on average. All right. So this one's always going to be tested against 0. Our comparison distribution is the distribution of means of difference scores. Distribution of means of difference scores. So we are, by calculating the differences, again, we are putting ourselves back into the single sample case. So our mu is, under the null hypothesis, 0. They tell me the standard deviation, the variance, not standard deviation in this case, the variance is, where is it? For the difference scores, so the population of individuals, 50. So that I have to convert to the, in this case, variance of, it's approximation, variance approximation for this distribution of means. So remember the formula up here, same as for the approximation as it is for knowing it exactly. Take the standard deviation. Sorry, I keep saying standard deviation. Usually we have standard deviation. In this case, we have variance divided by the sample size, which I don't remember. It is 10, sample size of 10. And then we get, of course, a 5. And so our approximation for the standard deviation of the distribution of means is the square root of 5, which I don't know, but we can certainly use our calculator. Square root for me is SQRT, and it'll show in the chat like, I'll say 2.24. 2.24. When we do it by hand, we don't really obsess over rounding errors. We understand that we're making rounding errors and take everything with a grain of salt. It's just the simplicity of doing it by hand. In reality, you won't do anything by hand. You have software, and then everything is very precise. So not a big deal. Just understand that rounding can create errors. When I'm slightly on the edge of making a decision one way or the other, I really do need to be much more precise. But the way the calculation is done is what we're focusing on now. So they want an alpha of 5%. Let's visualize what's happening here. Now this is the distribution of difference, not that wobbly, of difference scores. Okay, I'm clearly struggling with the nice curvature here. There we go. Small little bits in my drawing. No, try and get symmetry here. At least try. There we go. That's our t distribution for the means of different scores. That's going to be centered, assuming my null hypothesis is true, at 0. And I'm looking at, what did they say? High. So one-tailed on the right. So let's put our alpha of 5% over there. And this will be our t cutoff that produces that 5%. So that is linked to the choice of alpha. And our degrees of freedom is 1 less than the sample size, so a 9 in this case. And we look it up in our table. 9 degrees of freedom. So we're over here. One-tailed, alpha 5%, 1.833. 1.833. All right, 1.833. There we go. Now we want to see, what did we observe? We observed a mean of 3.8. So observed mean of 3.8, that tells me, when I standardize it, what is the observed t-score. This is a t-distribution as soon as I approximate the standard deviation. So I'll go to the formula here just to show you, formula sheet. We're still over here. We're still over here in formula 7.7. So we take our 3.8 and minus 0. I'll still say the 0 to fill in the formula completely. Under the null hypothesis, the distribution mean is 0, meaning no change, over our approximate standard deviation for this comparison distribution of 2.24. Let's go to our calculator and calculate that. I don't have to type in the 0 there. 3.8 divided by 2.24. And we get, if I round that, that's 1.7. 1.7. And then I can see, every example I pick is just not strong enough evidence. Oh, that's just bad luck. 1.7. I'm hoping to reject. I'm always hoping to reject, right? You want your treatment, you want your whatever you're implementing, your program, to have a change, to be worth it. But the evidence says maybe it is, but we can't tell. So, conclusion. Since our observed t-score is less than the cutoff to reject, we do not reject the null hypothesis. We can say a little more now. We don't have all the words because the story isn't really told for us here. But we can say something like the evidence is not, I'm just going to move this up a little while I write, not strong enough to suggest a change, let's say here, in, what shall we say, before versus after results. Again, I can be more specific here and talk about a treatment and so on if I knew the story, which I don't in this case because they just give me the information summarized. So I can't really be too wordy there, but the logic behind the hypothesis testing procedure is the same. So notice if you compare this to the previous example with a single sample t-test, you'll see here they don't give you a distribution mean because the distribution mean in the case of different scores is always 0 in the null hypothesis. So that's something to keep in mind. But other than that, I don't see much difference between this and the single sample t-test, making this fairly easy to get on top of. All right. Hopefully that helped to clarify things a little bit, just seeing how we talk through a problem. and go through the hypothesis testing procedure. We'll continue this and eventually see, well, what if the scores are independent? How do we go about things then? But that is for the next topic. See you then.